Welcome to WebAssembly and Nomad for next generation microservices. We're going to get started here by playing a little game. So take a look as we play Finicky Whiskers. All right, let's play Finicky Whiskers. This is a game about feeding a picky cat whatever food she wants at the moment. So she wants chicken. So we're going to click on this chicken button pretty much as fast as we can go. Oh, she changed her mind. Have you ever had a cat that does this kind of thing to you? Yes. So she's gone carrots for a long... Oh, now she wants fish. All right, chicken again. Now we're going a little bit faster. Oh, time is running out. Veggies again. Oh, beef way over there. All right. We're in the last 10 seconds of the game, and I'm still clicking on the wrong thing. Chicken now, and then beef again. And then carrots, vegetables. And there we go. About 108. That's a pretty average score. But that is Finicky Whiskers. Okay, well, you probably didn't come here to watch me play video games, but we will come back to Finicky Whiskers a little later on as we see how it's an example of a microservice written in WebAssembly. But what we are going to talk about today is WebAssembly and cloud services and why we think that WebAssembly is a great language for the next wave of cloud computing. We're going to talk about what WebAssembly is and why we picked it, how we run it in the cloud, and then we're going to really kind of zoom in on some performance and some speed issues at the end and see how we're running WebAssembly in Nomad and what kind of performance we get out of it and why we're excited about that. So my name is Matt Butcher. You might know me as the creator of Helm or the author of the Illustrated Children's Guide to Kubernetes. I led Deis Labs at Microsoft for a long time, and a bunch of us from Microsoft left and started a new company called Fermyon Technologies. And the reason we did is because we have gotten really excited about this idea that virtual machines and containers, they compose, they offer great things, compose the first couple of waves of cloud computing, but we think we identified some areas that neither of those can really kind of stretch or extend into. And we talk about this as the next wave of cloud computing. And we think that WebAssembly is really going to be the perfect fit for this next wave of cloud computing. So WebAssembly, you probably heard of it here or there. When you think about it, you're probably thinking about it in terms of the web browser. And what we've done is we've taken that idea and we've kind of extended it out beyond the browser. But let's take a look at just what WebAssembly is and what it's supposed to do and how it was designed. When Luke Wagner wrote the blog post to introduce WebAssembly just about 7 years ago, almost exactly 7 years ago, he said in that blog post, WebAssembly defines a portable, size and load time efficient format and an execution model specifically designed to serve as a compilation target for the web. So as this initial blog post introduced it, the real idea of WebAssembly was that it would extend the browser's language capabilities beyond JavaScript. Suddenly you could write web applications in Rust or in C or C++ or in Pascal or whatever language you could find that would compile to WebAssembly. So I happened to catch up with Luke at KubeCon in Valencia, Spain, and the two of us were talking, and I said, hey, I was going to use this quote from your old blog in my presentation at HashiCorp. And I said, so, does it ever surprise you that WebAssembly has kind of moved out beyond the browser? And he smiled and he said, well, we designed it to be really flexible, and we had always kind of hoped that it would find other applications beside the browser, but at the time we had a problem to solve and the browser was the way to solve it. And so, we are happy to see it kind of moving beyond. Now, this is important because Luke is a member of the Bytecode Alliance, and the Bytecode Alliance is a group of individuals and organizations, including like Intel and Microsoft and Fermyon and Fastly and Mozilla, that are all working together to try and build the technology that will give us a foundation for running WebAssembly outside of the web browser. And so Luke really is interested in seeing where this can go, as are we, and we're all kind of working together to figure out how to do it. Now, I did italicize one little bit of this quote because I think it's worth pointing out. It says, as a compilation target, right? There are a number of sort of misconceptions about what WebAssembly is. Some people will call it like the new version of Java, or a replacement for Flash, or some people will call it a separate programming language. Now, there's an element of truth in some of these things, but it's important to realize that those are all sort of like editorialization on what WebAssembly actually is. WebAssembly is a bytecode format that you can compile different languages to, and then execute it in any WebAssembly compliant virtual machine. So when you think about WebAssembly, think about it as a thing that you're compiling your programs into. Now, One of the things that excited us at Fermyon is that the technology, while born in the browser, really solved a lot of the same problems that we were experiencing in the cloud. Again, I'm from the Kubernetes ecosystem. I've been working in containers for the last 5, 6, 7 years. And we started to see issues as we tried to apply the existing technologies to nuanced user cases, right? And so we started looking and saying, okay, now if we can't accomplish these goals with virtual machines and we can't accomplish them with containers, is there a new wave of cloud computing technology that we could kind of fit in that would fill in this blank space where we just can't do these things yet today? And when we took a look at the problems that WebAssembly was solving for the browser, the surprising thing to us was many of those problems were the same problems we were experiencing in the cloud. For example, when we build containers that need to run in Windows and in Linux and in ARM and in AMD 64 and in i386, we found ourselves rebuilding the same container multiple times. Worse than that, we found ourselves actually having to edit the Docker files. So we were actually having to edit code in order to support different platforms. And this was getting kind of burdensome to the developer. To tell them, all right, to support these platforms, you're going to have to write a whole bunch of different versions of your build scripts. And what we wanted instead was something that was truly cross-platform, that could run on any OS, that could run on any architecture, and really to push beyond just the Linux and Windows and the AMD and ARM architectures, and to be able to do more exotic things like running on RTOSes in specialized chipsets. WebAssembly really bubbled up as that. And again, this is because in the browser, you don't want to give the user the experience that they download a WebAssembly module and it says, oh, sorry, you're on Windows, you can't run this web page, right? That has long ago been an unacceptable answer for the web. So again, the same virtues that made WebAssembly a good browser technology make it a good cloud technology. Another really big one for us was speed. One of the things that a virtual machine takes minutes to stand up. A container takes seconds to stand up. What we wanted was a technology that we could start nearly instantaneously, like milliseconds, microseconds instantaneously. And also we wanted binary sizes that we would be able to move around really fast in the data center. Now the reason why we wanted these things is because we're concerned with the cloud trend that we call overconsumption. And this trend is that in order to be scalable, right, you find yourself running long-running processes that consume CPU and memory, and they're consuming these resources all the time. So you might be running 5 replicas of the same service, and these 5 replicas are running across 5 different nodes all the time. So they're consuming resources all the time, which drives your cloud bill up, it drives the size of your VM up, it drives all kinds of things up. What we wanted to do was find a technology that would not have that characteristic, that would be able to start up and shut down so that on demand we could kind of scale up and handle a request and scale back down instantly. WebAssembly, again, because of the same characteristics of the browser, that people don't want to wait for things to be delivered and want things to start up and execute very quickly, those virtues translated well into the cloud. Finally, security sandbox was a really big deal to us. We wanted, of course, it's basically table stakes for the cloud, right? And for the browser too. When you download a web page from the browser, you don't want to have to worry that that web page might somehow root your system and start mining cryptocurrency and all that kind of stuff. And so a security sandbox in the browser is a big deal. Likewise, a security sandbox in the cloud is a big deal because when you're hosting executable code from other people, you don't want to run the risk that those other people might have malicious intent and be able to sort of root your servers and use it for nefarious purposes. So security sandbox from WebAssembly really sort of translated well into the cloud environment, and particularly so because WebAssembly's security model is capabilities based. In other words, you grant modules just the permissions that they need in order to execute, and we really liked that model. So we've kind of seen what WebAssembly is. When we talk about running WebAssembly in the cloud, what do we mean? What does it take to run WebAssembly in the cloud? Now, Fermyon's first really big open source project was the Spin framework. Now, Spin is a framework for building microservices and web applications in WebAssembly using sort of like a functions as a service style of model. Spin comes with a simple client experience. You can basically create your first Spin app by doing spin new and then the language you want to use and create a new application, and then spin build dash dash up and it'll build it in whatever language you've chosen and then start up a local web server. So we've worked really hard to build this sort of like great developer experience, this great local development environment that'll help you get started with WebAssembly very, very quickly. And you can be 0 to up and running in just a couple of minutes. Now, microservices and web applications were our big interest. These are the things we really wanted to be able to do with WebAssembly. So the HTTP request response model baked in from the first day we started Spin. But as we got going, we realized there were other kinds of events that could also trigger Spin applications, including things like Redis events, which we'll see later on when we return to Finicky Whiskers, or cron-like scheduled tasks. And we even wrote sort of an extensible system so that you could bring your own kind of events and write an event handling code that would spin up a new WebAssembly module for you. And then finally, what we'll talk about in a couple minutes is Spin makes it possible to push these applications out into the cloud. So what does a piece of Spin code look like? Well, this is a very simple Go module written to be a Spin microservice. For the most part, it's fairly mundane Go code, right? We're just importing some core Go libraries. We import one Spin library, and then in the main function, we just write a simple HTTP request and response handler. And this one, in this case, just says hello Fermion when you run it. So if you were to run this, you'd hit the HTTP endpoint and see hello Fermion show up on your screen. Now, importantly, what's missing here that you would normally write when you write a microservice? There's no logic here to stand up a web server. There's no port configuration, IP address configuration. There's no interrupt handling. There's no SSLs configuration. All of that is handled by Spin itself. All you have to do as the developer is write these kind of event handlers style request response HTTP handlers or Redis handlers or whatnot. So that's the local development experience as you get writing Spin applications. Now, at some point, you're going to finish your application and you're going to want to deploy it. And that's where Fermion Platform 1 comes in. So I'm excited to say that this was released today. And Fermion Platform 1 is our PaaS-like experience. You can think of it like, sort of like Heroku for WebAssembly functions as a service, right? Where you're just writing these functions, serverless functions, and you're deploying them out in sort of a Heroku-style workflow where there's a web UI called Hippo that allows you to set the environment variables, configure some things, promote it from dev to stage to prod, and so on. There's a package management system called Bindle that's running in the backend. You don't even have to really know how it works or that it's there because Spin and Hippo together deal with that in a way that's transparent to you. But then you have versioned releases and source control, version management control in there. Finally, Platform 1 runs on top of Nomad and Consul and Vault, and we have an easy deployment script that'll set you up with an HA environment for running Platform 1 in production. So if you want to learn more about Platform 1, you can head over to fermion.com. There's a link at the bottom of this page, but if you just go there and click on blog, this is the #1 blog post today. All right, so we've talked about what WebAssembly is and why we think it's the right fit for the cloud. But let's return back to the really important thing, right? Let's go back to the Finicky Whiskers game, and let's talk about what it takes to feed this cat whatever the cat is craving at the moment. So Finicky Whiskers is actually designed to be an exhibit of how to run WebAssembly in the cloud. And it's also designed to show you how we can make containers and WebAssembly sort of interact together. And all of this is run inside of a Nomad cluster. Okay? So when we play the game, we're involving about 7 different microservices. We'll talk about 5 today. There are 2 that are just sort of mundane ones, right? One handles things like HTTP redirects, but really 5 account for the gameplay of Finicky Whiskers. And then on top of that, we've got 1 container that's running Redis, and we're using that for both key value storage and for PubSub. And all of this is running in a 3-node Nomad cluster running on AWS using T2 small instances. So we're talking about a very svelte configuration in order to run this Finicky Whiskers game. So I overlaid the architecture diagram sort of over the UI for the game so you can kind of see and refresh your memory about how the UI works. Let's talk about what these microservices do when you play the game. Now, the first thing is you're going to go to finickyWhiskers.com and you're going to load the game. So when you load the game, you're getting the index.html, the CSS files, some JavaScript, a whole bunch of images, about 30 requests all in all. Each of those requests is going to an instance of the file server WebAssembly module, which is just serving that file back to the browser. Now the browser is going to take all those assets and render the page, and you're going to get this big giant start button in the middle. When you click on that, it fires off an HTTP request to the session microservice. The session microservice running in Nomad is going to issue a new session ID and some timing information and send all of that back to the browser. So that only gets called once, but then the timer starts ticking down in the browser, 30, 29, 28, and you're off to the races clicking chicken, 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 fish, 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 and trying to feed Slats the cat as she keeps changing her mind about what she wants to eat. Now, each of those clicks results in an HTTP request to the tally microservice. The tally microservice gets the data about what you clicked and what your ID is, and it looks at that and says, okay, user clicked chicken, chicken was the correct guess, so I'm going to push this onto the scoring queue in Redis. Oh, user clicked fish, that was incorrect, I'm going to throw this one out, right? So the things that get pushed onto the Redis queue are the scoreable items, and then tally exits. Now, on the other side of the Redis queue, Morsel is listening for new events. Each time a new event comes in, a new instance of the Morsel WebAssembly module is executed by Spin. And it's consuming off this event and saying, all right, I'll pull out the scoreboard, add one to the chicken score, and then, exit. And so the scoreboard is getting updated by Morsel. Now, 30-second timer, every time the timer ticks, the browser is issuing a new call to the scoreboard saying, hey, I need to update the score. What's the score? And scoreboard is grabbing the current scoreboard out of the key value storage. The same score that Morsel just updated, scoreboard is going to fetch back out and deliver back to the browser, and it's going to update that score in the upper right. So what we see there is the full gameplay executed as 5-ish microservices and this container running Redis. Now we're scheduling all of that out onto a Nomad cluster. You've probably seen containers being scheduled before, so I'm not going to cover that at all. When we got started, and again, we're all coming from the Kubernetes background, right? So we're used to writing very gigantic YAML files and things like that. It took us many, many months to get any WebAssembly stuff running in Kubernetes. We were so excited when we started with Nomad. Our first attempt to run all of this stuff just uses the exec driver. Finicky Whiskers today is actually still using just the exec driver to spin up a new Spin instance. Where we spent 6 months building Crustlet for Kubernetes in order to run WebAssembly in Kubernetes, it literally took us only a couple of days to get Spin running inside of a Nomad cluster. So we have we're just over the moon with how happy we are with the way this works. What you see here, though, is sort of an experimental Nomad task driver that we're currently working on that exposes Spin as a first-class task driver. And you can see that the configuration for standing up a WebAssembly application, and again, an application in WebAssembly can be many, many, many microservices, like Finicky Whiskers, which is 7. Stands up an application inside of a Spin instance running inside of a Nomad cluster. So let's take a view at the dashboards and kind of get an idea for what our infrastructure looks like while we're playing Finicky Whiskers. So I told you before, we're essentially running all of Finicky Whiskers on a group of 3 AWS T2 small instances. And you can see here on the Nomad dashboard sort of how that breaks down. We got about 17 allocations running there. A couple of them are Redis instances. I believe that we're running dev stage and prod all on the same T2 small cluster. So you'll see a whole bunch of allocations here that are dedicated to all these different ways of running Finicky Whiskers. All in all, one of the important things here is all in all, we're probably running close to 50 WebAssembly modules on these 3 T2 instances. And you can see the load is still quite manageable, right? Nothing's being strained and nothing's being stressed. So let's dive in and look a little more specifically about what it looks like when we're running Finicky Whiskers. So I happened to grab this snapshot while a couple of people, I don't even know how many people were playing Finicky Whiskers when I grabbed it. I just went to the live server and grabbed some data off of it. And you can see kind of 2 graphs here, right? On the left side, you see the CPU graph, which looks very, very spiky. On the right side, you see the memory one, which just looks like smooth and solid. So what's going on there, and how is WebAssembly running in such a way that it delivers this particular kind of profile? So first of all, memory usage. With Spin, we try and preload as many of the WebAssembly modules into memory as we can, because that shaves our startup time from a couple of milliseconds to microsecond time frame, right? We're just able to spin them up very, very 100 microseconds or something like that to get the execution going, right? And then we're executing the application from there. So the trade-off there is we need to consume some memory up front so that we can cache these things in memory. And the nice thing, though, is that we know kind of ahead of time how much memory we're gonna consume. So our memory usage ends up being predictable and pretty much flat level. Now, if we really zoomed in on this, we would see little tiny blurps as the game was played, as a little chunk of memory got invoked in order to serve up some files, or another little chunk of memory got invoked in order to handle a tally event or something like that. But at this level, it just looks smooth. Contrast that with the CPU one, which looks fairly jagged. Right? If you can see all those little tiny jags down there, those likely correlate to one individual WebAssembly request. You know, someone's clicking tally or morsel's getting run or something like that. And you just see CPU used in order to start up that module, execute it to completion, and shut it down. And because that's a matter of milliseconds, right? 10 to 50 milliseconds-ish, you're just seeing a small spike because it happens and then it's freed up again. And likewise, as the server starts to come under load and multiple people are playing at the same time, you start to see bigger spikes as multiple people are invoking modules at the same time. There's a highly uncommon tall spike in the middle, and I'm glad that I happened to capture this. This very likely shows a couple of people downloading the game at the same time, where they're generating somewhere in the 50 to 60 different requests in a very short window of time, and you see the CPU kind of spike. But even so, it doesn't really spike above the 60% case. Now, as we've looked at Finicky Whiskers, you're probably thinking, all right, this is a lot of microservices for a little game. You probably could have done the whole thing in browser, right? But the point of Finicky Whiskers was to exhibit the kind of runtime profile of WebAssembly and why we're so excited about it. So in a way, Finicky Whiskers is a game, but in another way, it's the world's most adorable manual load generator, because every time you're clicking, you're generating load on the Finicky Whiskers Nomad cluster, and we're kind of seeing how that interacts and what our limits are and how well it scales and so on. So in a typical game of Finicky Whiskers, how much load are you generating? So it seems to me that the average score of Finicky Whiskers is right around 100. I think my top score is about 134. We have 334 was the high score until a couple of days ago when we verified a 12-year-old scored over 500 on Finicky Whiskers. I'm not ever going to play video games against him because that's a pretty phenomenal score. But still, 100 seems to be about the average. So let's assume 100, and let's say, all right, how much load did we generate? Well, there are about 30 assets that have to get transferred. The index, CSS, HTML, JavaScript image files. They're about 30 assets. So that's 30 invocations of a WebAssembly module. That's 30 times that a module was started up, run to completion, and shut down. Then when we start that session, we only generate one invocation. Then every time we click, we're generating a tally request. And the tally request, if we're successful, is then putting something on the pub sub queue, which causes a morsel request. So for every one click, we're essentially starting and executing 2 WebAssembly modules. Then that scoreboard is ticking down, 30, 29, 20, and as it ticks down, it's calling scoreboard every time, once per second, and then once more at the end of the game. So sum total, in an average game with about 100, a score of about 100, we're executing 262 WebAssembly modules. Now, why is that number interesting to us? Well, because we're supposed to be exhibiting what makes WebAssembly a new wave of cloud computing, right? We're talking about being able to shut services down, start services up, and do all of this very, very rapidly. Now again, we contrast that with the container model that consumes resources, maybe over-consumes in many cases, and that's the kind of model we're trying to augment, right? So in this case, it is a good thing to see 262 modules starting up and shutting down in under 30 seconds. If we were to compare this with container technologies, could we even start up and execute to completion 262 containers in 30 seconds? That kind of illustrates why we think WebAssembly is promising as this new wave, this third wave of cloud computing. All right, so where do you go from here? Well, the first thing you can do is you can go try Finicky Whiskers. You head over to finickyWhiskers.com, play a couple of games of it, help us generate some load, see how much it takes for us to push out of T2 small instances and either, scale horizontally or scale vertically into T2 mediums or something like that. Just playing is great for us because it helps us gain more metrics and learn more about the system we're building. If this whole WebAssembly thing is new for you, one good place to go to get a deeper introduction to WebAssembly is the Fermyon.com blog. There's a post on there called An Introduction to WebAssembly and Cloud. The link is right there on the screen. And that kind of gets you up to speed on what WebAssembly is and again, why we think it's a promising technology on the cloud side. Now, Spin, we looked at that a little bit today. Spin.fermyon.dev has a quick start guide that'll get you going if you want to experience that developer experience in 5 minutes or less. And then today we introduced the Fermyon Platform 1, which is the PaaS style system. Our goal for Platform 1 has been that it should be installable in under 15 minutes, and that in just a couple minutes you should be able to get your first Spin application deployed up into a Nomad cluster running Spin with that Hippo UI. So if you want to learn more about the Fermyon Platform 1, best place to go right now is our blog. It's right at the top of the blog. First blog post is called Introducing Fermyon Platform 1, and you can read through that and get the lay of the land. Now, if all this WebAssembly stuff is not new to you, but the Nomad stuff is new for you, let me tell you about Nomad and why we're so excited about it. You can learn more about Nomad at nomadproject.io. But again, as Kubernetes developers, we came to Nomad saying, we need something that's gonna be a scheduler for this next wave of cloud computing. We can't make it work with Kubernetes. We've tried, we're all Kubernetes experts. And we were delighted to discover that we could do it with Nomad. The way that Nomad's jobs and task systems work, it's been really easy for us to schedule up these WebAssembly runtimes. And as you saw today, we can orchestrate our WebAssembly runtime alongside the container system, be able to use service discovery for them to figure out the configurations of each other, and then be off to the races. So that's why we chose Nomad as our scheduler for Project 1 or for Platform 1, and that's why we use it as we run Finicky Whiskers or our website fermyon.com or any of the other stuff that we manage online. With that, I think we are at game over. And so thank you for attending the talk. I hope you learned something, and thanks for having me.